You think reality works the way you see it. Table, chair, you. One place, one time, simple. But fire an electron at two slits and watch what happens. It goes through both. Not maybe, not theoretically. Actually, through both slits at once. The same single particle creating an interference pattern like a wave crashed into itself. How? Why does matter break every rule when nobody's watching? Thomas Young proved it in 1801. Bright English physician turned physicist, 38 years old, standing in a room in Somerset. He fired light through two slits cut in a barrier, expected two strips on the wall behind, and got bands. Bright, dark, bright, dark. An interference pattern. Waves do that. Water waves spread from 2 points and collide. Peaks meet peaks and make bigger waves. Peaks meet troughs and cancel out. But light? Isaac Newton said light was particles. Young's experiment killed that theory. Light was waves after all. The Royal Society watched those bands form on the wall and had to admit Newton got something wrong. Wave theory won, until 1905. That year Albert Einstein explained the photoelectric effect. Shine light on metal and electrons pop out, but only if the frequency is high enough. Doesn't matter how bright the light is. Low frequency never works. High frequency always works. Einstein said, light comes in packets. Quanta, little bullets of energy. Each photon carries energy equal to its frequency times a constant. Max Planck's constant, 6.6 to 6 times 10 to the negative 34 joule seconds. Light was particles again, but Young's interference pattern was still real. Both experiments worked. Light had to be both wave and particle. Wave-particle duality. Physics had a problem. If you value documented quantum history and cutting-edge experimental physics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual. Using sources from the 2019 Nature Physics study by Yakov Fein and colleagues at the University of Vienna showing interference with molecules of nearly 2,000 atoms published September 23rd. And the 2025 Science Daily report covering Stanford's demonstration of superposition over 54 centimeters with rubidium atoms. Now back to the information. 1926. Austrian physicist Erwin Schrödinger working in the Swiss mountains. Zurich, he's 39, developing an equation that will define quantum mechanics. Not the first try. Werner Heisenberg beat him to a quantum theory in 1925 with matrix mechanics. German, 23 years old. Matrices instead of waves. Schrödinger didn't like it, wanted something simpler. Took Louis de Broglie's idea that particles have wavelengths, matter waves. Built a differential equation governing those waves. Published it in January 1926, Annalen der Physik, the Schrödinger equation. A wave function that evolves over time. Describes every possible state a quantum system can be in, not where a particle is, where it might be. Probability waves. Max Born figured out what the wave function meant, German physicist. 43 years old, Göttingen University, June 1926. Published interpretation. The wave function squared gives probability density, where you'll likely find the particle when you measure it. Not where it actually is before measurement. Before measurement, the particle exists in superposition. All possible locations at once, all possible states simultaneously. Wave function contains everything. Schrödinger himself tried to interpret his equation differently. Thought the wave function represented actual charge density spread through space. Wrong. Experiments didn't match. Born's probability. Interpretation worked. Still works. Every quantum prediction for 99 years based on it. Here's where it gets strange. The act of measurement changes everything. Before measurement, a particle in superposition occupies multiple states. Measure it, and the wave function collapses. Instantly, from spread-out probability cloud to single definite value. One location, one momentum, one energy state, but during superposition, the particle genuinely exists in multiple states. Not that we don't know which state. The particle itself hasn't chosen. Niels Bohr and Werner Heisenberg developed the Copenhagen interpretation to explain this. Denmark. 1927. Bohr was 42, Heisenberg 25. Complementarity principle. Bohr presented it at a conference in Como, Italy in September. A physical phenomenon expresses itself differently depending on measurement apparatus. Light shows as waves or particles, but never both simultaneously. You can measure position precisely or momentum precisely, but not both. Uncertainty isn't about measurement tools being crude, it's fundamental. Nature itself is undetermined until observation forces a choice. Albert Einstein hated it. Famously declared, God does not play dice. 1927, Solvay Conference in Brussels. October, Einstein and Bohr debated quantum mechanics. 29 of the world's top physicists in one room. 17 were or became Nobel Prize winners. Einstein kept presenting thought experiments trying to prove quantum mechanics incomplete, trying to show particles must have definite properties we just can't access, hidden variables. Each morning Einstein proposed a paradox. Each day Bohr solved it. One time Bohr used Einstein's own general relativity against him. The debates continued through 1930 at another Solvay conference. Einstein never accepted quantum superposition as final truth. Spent the rest of his life searching for a deeper theory. Died in 1955 without finding it, but superposition kept proving itself. 1927, Clinton Davison and Lester Germer at Bell Labs, New Jersey. They fired electrons at a nickel crystal. Electrons made an interference pattern, just like light through Young's double slits. Same year George Paget Thomson in Scotland. Aberdeen University. He also got electron interference using thin metal films, particles acting as waves. Both won the Nobel Prize in 1937. Thomson's father, J. Thomson had won the Nobel in 1906 for proving electrons were particles. The father proved electron was particle. Son proved electron was wave. Both right. The double slit experiment moved to single particles. Richard Feynman predicted it in 1963. Volume 3 of the Feynman Lectures on Physics. American physicist, 45 years old. Caltech, described firing individual electrons through double slits, one at a time. Said each electron would still create interference pattern after many shots. Called it a phenomenon impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. Feynman said it was impossible to actually perform because the scale was too small. He was wrong about impossibility. 1974, Giulio Pozzi and colleagues at University of Bologna, Italy performed it. Single electrons through a biprism. Biprism acts like double slits for electron optics. Interference pattern built up electron by electron. Each electron went through both paths simultaneously. Experiments scaled up. 1999, buckyballs. Buckminster fullerene molecules. Each contains 60 carbon atoms. University of Vienna, Austria. Anton Zeilinger's team sent buckyballs through diffraction grating, got interference. Each molecule, 0.7 of a nanometer diameter, 500,000 times larger than a proton, visible in electron microscopes, still showed quantum behavior. 2012, same lab, molecules with 430 atoms. Phthalocyanine derivatives, still interference. Mass over 6,000 atomic mass units. 2019 brought the record. University of Vienna again. Marcus Arndt's team with Marcel Mayer from University of Basel synthesizing molecules. Published Nature Physics, September 23rd. Molecules called oligotetraphenyl porphyrins enriched with fluoroalkyl sulfonyl chains. Up to 2,000 atoms, mass over 25,000 atomic mass units, more than 25,000 times heavier than hydrogen. Molecular formula for the largest one, C707H260F 908 N16 S53 Zan4, over 40,000 protons, neutrons, and electrons total. De Broglie wavelength smaller than diameter of single hydrogen atom. They built a 2-meter-long interferometer, had to account for Earth's rotation and gravity in the design, kept molecules fairly warm for quantum experiment, around room temperature, still got interference. Superposition maintained for over 7 milliseconds. Long enough to set new bounds on alternative theories that predict wave function collapse based on mass. Different team, different record. Stanford University. 2015 but published results created attention. They used 10,000 rubidium atoms, not individual atoms. Bose-Einstein condensate, cloud of atoms cooled to near absolute zero, few millimeters across. Put in 33-foot tall vacuum chamber. Lasers pushed cloud up while splitting it into 2 quantum states. When atoms fell back down, they returned as one state but had arrived from 2 heights, 54 centimeters apart. 21 inches. Superposition maintained over that distance. Remained in superposition about 1 second, 4 times longer than previous demonstrations. Largest spatial separation for quantum superposition ever achieved. Why don't we see superposition in daily life? Decoherence. Quantum system interacts with environment. Air molecules, photons, heat, vibrations, anything. System becomes entangled with environment. Wave function spreads into surroundings. Coherence between different parts of superposition decays exponentially. System starts behaving classically. The more massive an object, the faster decoherence happens. The more interactions with environment, the quicker superposition vanishes. Dust grain floating in deep space far from any star would lose superposition of two locations within microseconds. Not because of collapse, because environment measures it constantly. Information about position leaks into surroundings. The mathematics explains why. Wave function describes system plus environment together. Total wave function never collapses under standard quantum mechanics. Keeps evolving according to Schrödinger equation. But when you trace out environmental degrees of freedom, you get reduced density matrix for system alone. Off-diagonal elements decay. Those elements represent quantum coherence, interference terms. They vanish exponentially with characteristic decoherence time. What's left looks classical. Diagonal density matrix, probability distribution over definite states. No interference, no superposition from perspective of system alone. But total wave function still contains correlations, information spread into environment, irreversible in practice. Too many degrees of freedom to track. Can't gather all environmental information back. Decoherence effectively permanent. First clear theoretical work on decoherence came 1970. German physicist H. Dieter Zeh, University of Heidelberg. He showed environment causes apparent collapse without actual collapse. System and environment become entangled. Appearance of definite outcomes emerges. Explains classical limit, explains measurement problem partly. Not complete solution, because doesn't explain which outcome occurs, just explains why outcomes appear definite. Wojciech expanded theory in 1980s and 90s. Polish-American physicist, Los Alamos National Laboratory. Developed Einzellection, environment-induced superselection. Certain states called pointer states resist decoherence better than others. Environment selects which basis becomes classical. Position basis for massive objects. Energy basis for photons. Explains why we see positions, not superpositions. Experimental verification followed. Serge Haroche at École Normale Supérieure in Paris. 2001 experiments. Trapped photons in microwave cavity between superconducting mirrors. Watched quantum state decay. Measured decoherence in real time. Single photon in superposition of different numbers. Cavity designed to minimize environmental interaction, but not perfect isolation. Residual interaction with cavity walls. Thermal photons in environment. State decayed exactly as decoherence theory predicted. Exponential loss of coherence, off-diagonal density, matrix elements vanishing. Won Nobel Prize 2012 for these measurements. David Wineland at NIST did complementary experiments. Trapped ions instead of photons. 1996 onward. Used beryllium ions in electromagnetic trap. Laser cooling to near ground state. Put in superposition of internal energy states. Watched decoherence from collisions with background gas, from electric field fluctuations, from laser phase noise, measured coherence times, improved isolation, extended coherence, showed decoherence controllable with better engineering. Also won Nobel 2012. Their work proved decoherence theory correct in detail, showed exactly how environment destroys superposition. Coherence, time defines how long quantum system maintains superposition. For large molecules at room temperature, it's femtoseconds, quadrillionths of a second. For superconducting qubits in quantum computers at near absolute zero, it's microseconds to milliseconds. Trapped ions can reach minutes. Record is 23 minutes achieved in 2023 with ytterbium atoms. 10,000 atoms maintained in superposition. But that required extreme isolation, ultra-high vacuum, electromagnetic shielding. Temperatures a fraction of a degree above absolute zero. The second you let environment in superposition dies, different systems decohere at different rates. Photons barely interact with anything. Travel through vacuum essentially forever, without decoherence. Hit atmosphere and scatter, hit detector and get absorbed, but en route, nearly perfect coherence. That's why quantum communication uses photons, long coherence length. Electrons more problematic. Charge means electromagnetic interaction, scattering from other charges, easy decoherence, neutral atoms better, less interaction, but still magnetic moments, still polarizability. Superconducting circuits, charge-based but shielded, kept at millikelvin temperatures, 20 millikelvins typical, reduces thermal excitations, extends coherence to useful timescales. Numbers matter. Decoherence timescales inversely with coupling to environment. Strong coupling, short coherence. Weak coupling, long coherence. Also scales with number of environmental degrees of freedom. More ways to interact means faster decoherence. Also, temperature matters. Higher temperature, more thermal photons, more molecular motion, faster decoherence. Formula exists. Decoherence rate proportional to temperature times. Coupling strength times density of environmental states. Can calculate decoherence time for any system. Predictions match experiments when done carefully. 1991 brought another milestone. Olaf Karnel and Jörg Mlinek, University of Konstanz, Germany, double slit with atoms. Not electrons or photons, actual atoms. Metastable helium, passed through micrometer scale slits in gold foil. Got interference pattern. Atoms wavelength around 50 picometers. Slits 1 micrometer apart. Interference fringes visible. Clear demonstration atoms are waves. Atoms have mass. Still show wave nature. Still superposition through both slits. Published in Physical Review letters. Confirmed de Broglie matter waves for neutral atoms. 2002 brought electrons through real double slits. Not biprism. Actual pair of slits, nanofabricated in material. Stefano Fraboni and colleagues. University of Modena, Italy. Published 2012, but experiment done earlier. Slits cut using focused ion beam. Width about 100 nanometers. Separation 200 to 400 nanometers. Electron beam incident. Collected transmitted electrons with single electron detector. Built up interference, pattern electron by electron. Exactly as Feynman described. Each electron goes through both slits. Wave function splits, recombines, interferes. Pattern emerges statistically. No electron sees others. Each acts as wave individually. Original Feynman thought experiment finally realized precisely as proposed. Interference visibility matters. Perfect interference gives maximal contrast between bright and dark fringes. Visibility equals maximum minus minimum intensity divided by maximum plus minimum. Perfect visibility equals 1. No interference. Visibility equals 0. Decoherence reduces visibility. Partial path information reduces visibility. 2019. Vienna experiment achieved 90% visibility. Very high. Nearly perfect interference despite molecule size and complexity. Shows superposition maintained despite environmental threats. This creates the measurement problem. When does superposition end? Where's the boundary between quantum and classical? Schrödinger illustrated the absurdity in 1935. His cat thought experiment. Published in German journal Naturwissenschaften. November issue, cat in sealed box with quantum-triggered poison, radioactive atom that might decay. 50% chance per hour. Geiger counter detects decay and releases poison-killing cat. Quantum mechanics says atom is in superposition of decayed and not decayed until measured, so cat is in superposition of alive and dead, both states simultaneously. Open box and wave function collapses. Cat becomes definitely alive or dead. Schrödinger meant it as criticism, thought it showed quantum mechanics was incomplete, but the math says he's right. If quantum mechanics applies to everything, then cat really is in superposition. We just never see it because decoherence happens too fast. Practical question arises. What counts as measurement? Does detector need to be conscious? No. Any interaction causing decoherence works. Geiger counter measures atom. Counter is macroscopic, has enormous number of internal degrees of freedom. Atom state gets entangled with all those degrees. Information spreads. Irreversible. That's measurement. No consciousness needed. But then, when does measurement happen? When photon hits atom. When electron cascade starts in detector. When current flows. When display lights. No sharp boundary. Progressive entanglement. More and more degrees of freedom involved. Superposition fades gradually. Becomes more and more classical looking. Practical measurement occurs when enough entanglement exists that reversing process becomes impossible. Typically very fast. Nanoseconds or less for macroscopic detectors. John von Neumann analyzed this 1932. Mathematical Foundations of Quantum Mechanics. German-American mathematician. 28 years old. Princeton. Showed measurement requires cut between quantum system and classical apparatus. Cut is arbitrary. Can place it anywhere along measurement chain. Math works, same. But somewhere, transition from quantum to classical must occur. Where? Von Neumann couldn't say, became known as von Neumann cut, Heisenberg cut. Problem remains unsolved in orthodox interpretation. Decoherence helps explain appearance of cut, but doesn't eliminate arbitrariness completely. Different measurement schemes exist. Projective measurement, disturb system completely. Collapses wave function to eigenstate of measured observable, standard textbook measurement, but also weak measurement. Aharonov and colleagues developed 1988. Israeli physicist Yakir Aharonov with collaborators. Weak coupling between system and detector. Barely disturbed system. Gives tiny bit of information. Repeat many times on identically prepared systems. Build up statistics. Can infer properties that strong measurement would destroy. Allows peaking at superposition without fully collapsing it. 2007 experiments demonstrated weak measurement clearly. Lundin and Steinberg at University of Toronto, Canada, measured momentum and position of photons using weak measurements. Got information about both simultaneously. Violates uncertainty principle for strong measurements. But weak measurements, different. Trade precision for gentleness. Many repetitions needed. Works. Reveals properties that seemed hidden. Shows superposition structure in detail. Wave function mapping became possible. 2011, Lundin team directly measured photon wave function, not just inferred from statistics, actually measured it, using weak measurements, scanned through position space, got wave function values, published in Nature. First direct measurement of wave function. Confirmed theoretical predictions, exactly. Some physicists say wave function collapse is real physical process, GRW theory, Gherardi, Rimini, Weber. Proposed 1986, Italian physicists. Says wave functions spontaneously collapse at random intervals. Collapse rate proportional to mass squared. Heavier objects collapse faster. Explains why we never see macroscopic superpositions. But experiments testing this find no evidence. Particles stay in superposition longer than GRW predicts. Others say many worlds. Hugh Everett proposed it, 1957. American physicist, PhD thesis at Princeton, 27 years old. No collapse at all. Wave function never collapses. Every measurement causes universe to split. Each outcome happens in different branch. Electron goes left in one universe, goes right in another. Both real, both exist. Cat alive in one branch, dead in another. You see only one branch because you're entangled with measurement result. Your consciousness splits too. Other versions of you see other outcomes. Solves measurement problem by saying there is no collapse. Everything happens. Controversial, but mathematically consistent. Can't be proven or disproven because you can't access other branches. Bohmian mechanics takes different approach. David Bohm, 1952. American physicist working in Brazil, 44 years old. Published in Physical Review. Particles have definite positions at all times. Real trajectories guided by wave function. Wave function is real field that pushes particles along paths. Explains double slit by having wave go through both slits while particle goes through one. Wave guides particle to create interference pattern. Deterministic, no randomness. But non-local, particle's trajectory depends on wave function everywhere instantaneously. Faster than light influence, reproduces all quantum predictions, experimentally indistinguishable from standard quantum mechanics. Just different interpretation. Recent experiments probe deeper. 2016, Ryo Okamoto and Shigeki Takeuchi, Kyoto University, Japan. They tested predictions from Yakir Aharonov and Lev Weidman about weak measurements. Can peak at superposition without fully collapsing it. Used light-carrying circuit, quantum router where one photon controls root of another. Shutter photon and superposition simultaneously closed multiple slits. Weak measurement allowed inference of photon location at different times. Results match predictions. Particle really in multiple places. 2018, same team plus Avshalom Elitzer and Eliyahu Cohen, paper in Scientific Reports. May 18th. They proposed photon superposition might involve states even stranger than two places at once. Negative energy states, negative mass counterparticles. Idea is superposition averages over many weird states. We only see average. Post-selection measurement techniques might isolate those states. Revolutionary if true? Suggests superposition hides entire zoo of exotic states. Quantum mechanics averages over, still being analyzed, still controversial. 2023 brought another breakthrough. ETH, Zurich, Switzerland. Researchers put 16 micrograms sapphire crystal into superposition, 2 vibrational states. Mass involved roughly 10 to the 17th atoms. Published in journal Physical Review X. Largest object by mass ever put in quantum superposition regarding internal degrees of freedom. Not spatial superposition like Stanford experiment, but vibrational superposition. Crystal vibrating in 2 modes simultaneously. Macroscopic object exhibiting quantum behavior. Scale matters. The experiments prove superposition isn't limited to atoms. Works for huge molecules. Works for crystals. Works for clouds of thousands of atoms separated by hand-widths of distance. The question becomes, where does it stop? What's the limit? Is there a limit? Some theories say mass itself causes collapse. Gravitational self-interaction destroys superposition above certain mass. Roger Penrose proposed this. English physicist, 1996. Gravitational decoherence. When mass distribution in superposition creates significantly different gravitational fields, the spacetime itself can't sustain both states. Causes spontaneous collapse. Predicts collapse time proportional to mass. No experimental evidence yet supports this. Superposition. Experiments keep going to higher masses without finding collapse. Temperature critical. Hot objects radiate photons. Those photons carry information about objects' state. Information leaks into environment, causes decoherence. That's why quantum experiments happen at near absolute zero. Cool atoms to microkelvins or nanokelvins. Superconducting circuits operate at millikelvins, a few thousandths of a degree above absolute zero. Reduces thermal photon emission, reduces molecular vibrations, extends coherence time. 2019, Vienna experiment kept molecules at room temperature. Major achievement. Shows superposition survives even with thermal motion. Application side matters. Quantum computers rely entirely on superposition. Qubits in superposition of 0 and 1 simultaneously. Allows parallel computation. Quantum algorithm exploits superposition to test multiple solutions at once. Decoherence is enemy. Companies like IBM, Google, IonQ, Rigetti racing to extend coherence times. Superconducting qubits typically last microseconds to milliseconds. Trapped ion qubits can maintain coherence longer. Minutes under right conditions. Better isolation, better shielding, cryogenic cooling. All trying to keep superposition alive long enough to complete calculation. Specific numbers reveal progress. 2019 IBM quantum computer, 27 qubits, coherence time around 100 microseconds. 2023 IBM Osprey processor, 433 qubits. Coherence improved, but still under 200 microseconds for best qubits. Google Sycamore 2019, 53 qubits. Coherence around 20 to 30 microseconds. IonQ trapped ion systems, 32 qubits. Coherence exceeding 10 seconds. Orders of magnitude better. But slower gate operations, trade-off, fast gates versus long coherence, different approaches for different problems. Gates manipulate superposition. Quantum gates rotate qubit states. Hadamard gate creates equal superposition. Takes 0 to 0 plus 1 divided by square root 2. Takes 1 to 0 minus 1 divided by square root 2. Perfect 50-50. Superposition. C-NOT gate entangles qubits. Controlled knot. Control qubit determines whether target qubit flips. Creates entangled states from product states. Combination of single qubit rotations and C-NOT gates allows any quantum computation. Universal gate set. Algorithms exploit superposition cleverly. Grover's algorithm searches database. Classical search needs n steps for n items, average. Grover needs square root of n steps. Quadratic speedup. Uses superposition over all database entries. Amplitude amplification enhances correct answer. Shor's algorithm factors numbers. Classical factoring exponential in number of digits. Shor's polynomial. Exponential speedup. Threatens RSA encryption. Uses quantum Fourier transform. Requires superposition over exponentially many states simultaneously. Period finding reduces to superposition of all possible periods. Measurement collapses to actual period. That's the power. Superposition allows testing all possibilities at once. Error correction crucial. Quantum error correction codes protect superposition from decoherence. Encode logical qubit in multiple physical qubits. Redundancy allows error detection without destroying information. Surface codes most promising. Arrange qubits on two-dimensional lattice. Measure parity of neighboring qubits. Detect errors without measuring logical state. Correct errors before they propagate. Threshold theorem proved. If physical error rate below threshold around 1%, then arbitrarily long computation possible with enough qubits. Current systems approaching threshold. Google claimed below threshold 2023. IBM working toward it. Race to fault tolerant quantum computing. Error correction helps. Quantum error correction codes spread information across multiple physical qubits. Redundancy allows detection and correction of errors from decoherence. IBM demonstrated it 2023 with their quantum processor. Google's Sycamore processor in 2019 claimed quantum supremacy. Performed calculation no classical computer could do in reasonable time. Used 53 superconducting qubits. Maintained superposition long enough to complete task, 200 seconds. Classical computer would take 10,000 years, they estimated, though that estimate disputed deeper implications. Superposition forces us to rethink reality. Before measurement, particle isn't simply unknown. It genuinely doesn't have definite value. All possibilities exist simultaneously. Measurement doesn't reveal pre-existing fact. It forces nature to choose, creates fact that didn't exist before. Or, if you accept many worlds, creates all facts in different branches. Universe splits, all outcomes real. Or, if you accept Bohm particles always had positions but wave function non-locally guided them, different interpretations. Same mathematics, same predictions. Can't distinguish experimentally? John Stuart Bell proved something crucial in 1964. Irish physicist, CERN, 36 years old, Bell's theorem. Hidden variable theories must be non-local if they reproduce quantum predictions. Can't have both local realism and quantum mechanics. Experiments, since 1972 by Alain Aspic and others, confirmed quantum mechanics. Violated Bell inequalities. Local hidden variables ruled out. Reality is either non-local or not real until measured. Spooky action at distance or no properties until observation. Both options disturbing. Both confirmed by experiment. Einstein's local realism is dead. Bell inequality derives from local realism assumptions. Suppose particles have definite properties before measurement. Local hidden variables. Suppose measurement on one particle can't instantly affect distant particle. Locality. These assumptions together imply inequality. Statistical correlation between measurements can't exceed certain bound. Bell derived the bound, called Bell inequality. Multiple versions exist. CHSH inequality, most common. Clauser, Horn, Shimoni-Holt. Correlation function bounded by 2 in classical local theory. Quantum mechanics predicts violations. Correlation can reach 2 times square root of 2, about 2.8. Difference significant. Testable. First experimental test came 1972. Stuart Friedman and Clauser, Berkeley. Measured polarization correlations of entangled photons from calcium cascade. Got violation of Bell inequality. 2.7 plus or minus 0.05. Above classical limit. Below quantum prediction, slightly. Close enough. Suggested quantum mechanics, right? But loopholes remained. Detection loophole. Not all photons detected. Fair sampling assumption required. Maybe detected subset is biased. Locality loophole. Detectors not far enough apart. Maybe signal between them. Speed of light allows communication. Alain Aspect closed locality loophole 1982. Or say, France switched detector settings while photons in flight, used acousto-optic modulators, nanosecond switching. Photon pairs separated by 12 meters. Travel time 40 nanoseconds. Settings changed every 10 nanoseconds. No time for signal at light speed. Still got violation. 2.7. Quantum mechanics confirmed. Local hidden variables ruled out definitively. Aspect won Nobel Prize 2022 for this work, along with Clauser and Zeilinger. Confirmed non-locality is real. Information theory provides another view. Quantum mechanics as theory of information. Not physical objects, but information states. Wave function encodes information. Superposition represents our knowledge being distributed across multiple possibilities. Measurement updates information. Christopher Fuchs and colleagues developed this. Cubism, quantum Bayesianism, subjective interpretation. Wave function represents agents' beliefs, not objective reality. Controversial. Solves some problems, creates others. Debate continues. Current frontier. Researchers trying larger scales. Marcus Arndt at Vienna working on molecules with 10,000 atoms. Technical challenges enormous. Molecules that heavy hard to manipulate. Need precise control. Need isolation from environment. Need sensitive detection. Working on it. Others attempting spatial superposition of larger objects. Micron scale objects. Visible to naked eye. Not yet achieved. Decoherence too fast. But attempts continue. Testing quantum gravity might need superposition. Put massive object in spatial superposition. Measure gravitational field. See if gravity exhibits quantum behavior. If gravitational field is also in superposition, then gravity is quantum. If not, then gravity might be classical. Fundamental question. Experiments proposed but not yet feasible. Need better isolation. Need more sensitive instruments. Future experiments may answer whether gravity itself quantum or classical. Recent theoretical work explores connection between superposition and spacetime. Some models suggest spacetime emerges from quantum entanglement. Area of spacetime related to amount of entanglement. Superposition fundamental. Spacetime derived. Speculative but mathematically consistent. String theory, holographic principle, gauge gravity duality all point this direction. Superposition might be more basic than space itself. Biology intersects quantum mechanics. Photosynthesis uses quantum superposition. Light harvesting complexes in plants, chlorophyll molecules, excitation energy and superposition across multiple pathways simultaneously. Explores all routes. Finds most efficient. Confirmed 2010 experiments by Graham Fleming at Berkeley. Room temperature, quantum coherence in biological system. Survives hundreds of femtoseconds. long enough to matter, evolution exploited quantum mechanics. Birds might use quantum effects for navigation, magnetic sense, radical pair mechanism in retina, electrons in superposition. Orientation depends on magnetic field. Disputed, but evidence growing. Quantum measurements became practical. 2012 Nobel Prize awarded for methods measuring quantum systems without destroying them. Serge Haroche and David Wineland, French and American. They developed techniques to observe quantum states without collapse. Weak measurements, non-demolition measurements, allows watching superposition evolve, crucial for quantum computing, allows error detection without destroying information. Philosophical implications run deep. Measurement problem remains unsolved. How does classical world emerge from quantum substrate? Why do we see definite outcomes? What counts as measurement? Must observer be conscious? Probably not. Any interaction that causes decoherence works. But where exactly does quantum end and classical begin? No sharp boundary found. Appears to be smooth transition. More interactions means more decoherence, means more classical behavior. Never complete transition. Always some quantum effects remaining, but unmeasurably small. Alternative approach, consistent histories. Robert Griffiths, 1984, American physicist. Assign probabilities to sequences of quantum events. Histories, different decompositions of history possible. Must choose consistent framework. Rules about which histories can be combined. Avoids collapse. Avoids many worlds. Treats different times democratically. Still controversial. Not widely accepted, but logically consistent. Some experiments test superposition limits. Collision models. Flying particles through gas. See how quickly superposition destroyed. Measure decoherence rates. Compare to theory. 2017 experiment by Lucas Meyerhofer in Vienna. Sent molecules through dilute gas. Measured how collisions destroyed interference. Tested decoherence models. Results matched quantum predictions. Ruled out some alternative theories. Recent proposals suggest testing superposition with viruses. TMV tobacco mosaic virus, 300 nanometers long, 10 million atomic mass units. Far bigger than anything tried. Groups in Vienna and elsewhere designing experiments, cool viruses, put in superposition, measure interference, hasn't been done yet. Technical challenges, massive. But if achieved, would push superposition into realm visible under optical microscope. Dark matter detection might exploit superposition. Some models suggest dark matter particles create tiny kicks when passing through detector. Put detector in superposition. Dark matter interaction causes decoherence. Measure decoherence rate. Infer dark matter properties. Speculative, but worth trying. Quantum sensors using superposition already most sensitive instruments humans have built. Atomic clocks, gravitational wave detectors, magnetometers. All exploit quantum superposition for precision. Looking deeper at math. Superposition mathematically simple. Linear combination of basis states. Coefficient for each state complex number. Absolute square gives probability, but coefficients have phase. Relative phase between states creates interference. Explains double slit. Wave functions from two slits add. Phases line up constructively some places. Cancel destructively others. Creates pattern. Simple math. Bizarre implications. Wave function lives in Hilbert space. Infinite dimensional complex vector space. Each dimension represents possible state. Physical state is vector in that space. Superposition is vector sum. Measurement projects onto basis, collapses vector to single basis state. Probability from projection amplitude squared. Entanglement extends superposition. Two particles share quantum state. Measuring one affects other instantly regardless of distance. Einstein called it spooky action at distance. But it's not action. No information transmitted faster than light. Just correlations appear. Correlation stronger than classical allows. Bell inequality violations prove this. Entangled state is superposition over combined system. Can't write as product of individual states. Particles lose individual identity. System becomes whole. Measurement on one part reveals information about other, not because one sends signal, because they never had separate properties. They're entangled. Joint superposition. Practical quantum protocols use this. Quantum teleportation, transfers quantum state from one location to another, uses entanglement in classical communication. No faster than light signaling, but state gets moved. Achieved first in 1997, Anton Zeilinger's group, University of Innsbruck, Austria, teleported photon state, later done with atoms, with ions, with superconducting circuits. Works. Essential for quantum networks, quantum cryptography, exploits superposition, photon polarization in superposition. Eavesdropper must measure. Measurement disturbs superposition. Introduces errors. Legitimate users detect errors. No communication compromised. Provably secure communication. First commercial systems operating now. Several companies offer quantum key distribution. Banks and governments testing it. Superposition makes it possible. Timeline clear. 1801, Young proves wave nature of light. 1905, Einstein proves particle nature. 1926, Schrödinger describes superposition mathematically. Born interprets it probabilistically. 1927, Bohr and Heisenberg develop Copenhagen interpretation. Davison, Germer, and Thomson prove electron waves. 1957, Everett proposes many worlds. 1964, Bell proves non-locality. 1974, first single particle double slit with electrons. 1999, buckyballs show interference. 2015, Stanford achieves superposition over 54 centimeters. 2019, Vienna achieves interference with 2,000 atom molecules. 2023, ETH puts sapphire crystal in vibrational superposition, 124 years from Young to now. Theory refined. Experiments expanded. Mathematics deepened. But fundamental mystery remains. Why superposition? Why does universe work this way? No answer yet. Best we can say is nature operates by linear differential equations. Schrödinger equation is linear. Solutions add linearity, necessitates superposition, but why is nature linear at quantum level? Don't know. It just is. Experiments confirm. Predictions work. Technology depends on it. Understanding incomplete. Feynman said, I think I can safely say that nobody understands quantum mechanics. Still true. We can calculate, we can predict, we can build devices. But comprehending what it means for a particle to be in two places at once. No human intuition evolved for that. Our brains developed understanding middle-sized objects, rocks, trees, animals, never encountered quantum behavior directly. So we lack gut feel, can work the math, can run experiments, can't really grasp it deep down. Maybe that's okay. Maybe universe doesn't need to make sense to evolved apes. Maybe math is enough, but experiments continue. Researchers push boundaries, larger masses, greater distances, longer times, better isolation, more precise control. Each advance opens possibilities. Quantum computers getting better, quantum sensors getting sharper. Quantum networks spreading, all riding on superposition, all depending on particles being multiple places, all trusting math that defies common sense. Next decade may bring virus interference, may bring mechanical oscillator and spatial superposition, may bring test of quantum gravity, may bring quantum computer that solves problems no classical machine can touch. All requires maintaining superposition. All fights decoherence. All pushes against environment trying to force classical behavior. Nature provides the answer. Universe runs on quantum mechanics at bottom. Superposition and fundamental, not approximation, not mathematical trick, actual reality. Particles genuinely occupy multiple states until interaction forces choice, or branches, universe, or reveals hidden trajectory. Interpretation matters less than phenomenon itself. The thing that happens is real. How we explain it philosophically unresolved. But that it happens, established beyond doubt by 1,000 experiments over 100 years. Someone flipped a switch we never knew existed. Reality doesn't work the way it looks. Solid objects aren't solid. Definite positions aren't definite. Observer matters to outcome. Measurement creates reality, or reveals pre-existing non-local truth, or splits universe. All disturbing. All true in different interpretations. All make same predictions. All confirmed by experiment. And here's the cold reveal. Buried in data from 2019 Vienna experiment. Those molecules composed of 40,000 particles each. Mass spread over space. Interference pattern showing superposition maintained. The wavelength, smaller than hydrogen atom diameter, less than 1 angstrom, yet still wave behavior, still interference, still quantum. At that scale, theory says wave function shouldn't hold together. Thermal fluctuations should destroy it. Gravity might collapse it, but it doesn't. Superposition survives. Pattern remains. Wave function spreads across 2 slits separated by micrometers, even though particle itself is nanometers wide. Quantum mechanics says possible. Experiment confirms. No alternative theory fits data. Just quantum superposition, doing what math says it should. Being in 2 places at once because the universe allows it. Matter doesn't pick where it is until you make it choose.